exercise 4, and we're going to look at water waves. So this one states, if a water wave with length L moves with velocity v, so you have a length L here, and it starts moving with the peaks of it, moves with velocity v across a body of water with depth d, as in the figure below. So there's the height of this, and it's the average height of these peaks and valleys, or the height of the water when it's when there's no wave. So it's moving across here from the peaks like that. There's velocity v, and yeah, and then what we have is we'll have this formula for the velocity v. So v squared equals to g times L divided by 2 pi times tan of h, or tan h, or hyperbolic tangent of 2 pi d divided by L. So there's a big equation there. We're not going to derive that, but we're going to go and do some approximations with it. So part A of the question states, if the water is deep, show that V is approximately equal to square root of G times L divided by 2 pi. And then part B says, if the water is shallow, then use the Maclaurin series for hyperbolic tangent or tan H to show that V is approximately equal to the square root of G times D. And thus, in shallow water, the velocity of a wave tends to be independent of the length of the wave. There's no length here in shallow water. And then part C says, use the alternating estimation theorem to show that if L is greater than 10 times D, so yeah, so much greater than D, then the estimate of V squared is approximately equal to GD, that's just squaring these two sides, is accurate to within 0.014 G times L. So let's look at the solution and look at part A first. So solution. So if the water is deep, so here's the question right here. So if the water is deep, show that this approximation holds. So if the water is deep, then 2 pi d over L is large, because you'll have this water, this one is deep. So if this one is deep, you're going to have this value. Yeah, this 2 pi d over L is going to be much bigger than this capital L. And this term right here will be very, very large if this is deep. And also we know from my earlier video referenced below that the hyperbolic tangent of x approaches 1 as x approaches infinity. So you can get an idea of what kind of approximation we're doing. So if this is large, and we also know that as x approaches infinity, the tan goes to 1. So in other words, this tan would be going to 1. So here's from my earlier videos, definition of the hyperbolic functions. And so here is the YouTube link. It's one of my earlier videos. And here's notes archive. So definition of the hyperbolic functions, recall, just defined as, so sinh of x, or hyperbolic sine, is just equal to e to the x minus e to the negative x, all divided by 2. Then cosh is going to be a plus there. So you just have this e to the x plus e to the negative x, and all divided by 2. And then hyperbolic tangent of x is just equal to sinh divided by sinh of x divided by cosh of x. And just like basic trigonometry, but this is the definition. We start off for sine and cosine. And then the other ones are the same as the trigonometric ones, the basic ones. And yeah, so yours is going to be 1 divided by sinh of x, and this one's secant. It's going to be 1 divided by cosh of x, and so on. And this is the inverse of the tangent. So anyways, going for this recall from my earlier video, this is the graph of the hyperbolic tangent of x. So this is y equals tangent of x, and it looks something like this. So it goes to infinity. As x goes to infinity, this equals to 1 on the positive side. So thus we could use the following approximation for when the water is deep. And that approximation is just setting it equal to 1. So this is the hyperbolic tangent of x, or of 2 pi d over L. So if d is much bigger than capital L, so it's very deep, this is going to be approximately equal to 1. Thus, our formula. Yeah, so that's our formula over here. So v squared. V squared equals GL divided by 2 pi times tan h of this 2 pi d. So thus we have v squared, which equals 2. Remember, that's just GL over 2 pi times hyperbolic tangent of 2 pi d over L. This is going to be, now it's going to go to 1. So I'm just going to just double check again. So GL divided by 2 pi tan h, just 2 pi d. So that looks correct over there. So then this is going to be, well, this is just going to be approximately equal to G, because this is going to be equal to 1. Yeah, as that one is large, so this equals to 1. So this is just going to equal to GL over 2 pi. So in other words, when we square root it on both sides, so V equals 2, and we're going to look, it's going to be plus or minus to be mathematically complete. So it's going to be plus or minus, and then square root G over L 2 pi. And yeah, we also have to have this plus or minus, and we're just going to choose the plus. And that's because when you're multiplying, when you have a square root or a square, if you have 2 negatives, they become positive. So it's the same thing as if you have 2 positives or 2 negatives. So we're just going to keep it like that. But then we're going to choose the plus, just because that is what's used practically. But I just wanted to include that note there. So now it's going to be, yeah, so then now this equals to GL over 2 pi all square root. Let's write this better. And box this out. And this is exactly what we were asked to derive. So this is approximately equal to this one over there. Yeah, so there's a square root GL divided by 2 pi. And this is equals is actually approximation. So this equals to, yeah, this is approximately equal to this function there. Yeah, so that is what we have. And now let's look at part B. So let's go scroll up to part B. So it says, if the water is shallow, use the Maclaurin series for tan H to show that. Yeah, for a hyperbolic tangent of, or tan H to show that yeah, V is approximately equal to square root G over D. So now with this approximation, we get rid of this 2 pi there and the L. So we don't have, it's not dependent on the length. Yeah, so thus in shallow water, the velocity of a wave tends to be independent of the length of the wave. And yeah, so this is if the water is shallow. That is, L is large relative to D. Or actually rephrase better, just L is just, yeah, it's large, but not necessarily larger than D, because D, as long as this one is shallow, and yeah, with shallow water, you can still have small waves or large waves and so on. So anyways, let's go further. So now we're going to look at the Maclaurin series for hyperbolic tan of, yeah, hyperbolic tangent. So now let's go over here. So part B, the Maclaurin series requires the derivatives at x equals 0. That's just the Maclaurin-Taylor at a equals 0, which we can determine for tan H by first recalling the derivatives and identities of hyperbolic functions from an earlier video. So here's from my earlier video. Just put some screen grabs right here. This is in here, I just put a playlist one there just because it's from several videos. I used to do them one by one, and as opposed to what I'm doing right now, which is all at once. Okay, so derivatives of hyperbolic functions. Recall derivative of sinh of x is going to be cosh of x, so similar to regular trig derivative. So d over dx of cosh of x is equal to sinh of x, and then the tangent one, the one we're focused on, is going to equal to sinh squared of x. And also the derivative of this sinh of x is going to be negative sinh, or negative secant h of x times tangent of x. Yeah, or yeah, this is just how to pronounce it. Yeah, I mean, usually it's pronounced, yeah, I'm not trying to pronounce it. So I'm going to just call it hyperbolic secant. And yeah, the derivative of hyperbolic secant is equal to negative hyperbolic secant times hyperbolic tangent, or sec h. Anyways, and then the hyperbolic identities that I'm going to be using is over here. I'm going to be using this one mainly, just because the solutions manual would simplify over all of them to get to this tan h squared. Alright, enough of me talking. Let's go further. So thus we have f of x. So let's just take the derivatives because we want to get the derivatives at 0. So f of x is equal to tangent x like that, and now we want to get the first value, so f of 0. Well, we know from that graph it's equal to 0. This equals 0, or we could just calculate it because we know the definition here. It's going to be sinh over cosh. So this is going to be e to the x minus e to the negative x divided by e to the x plus e to the negative x, and then the 2's cancel out. So let's just write it down like that. This is going to equal to e to the this is going to e to the 0 minus e to the negative 0. This will be a sign on the top, and then divided by 2, and then the top's 2, they'll just cancel. And this one here is going to be e to the 0 plus e to the negative 0. So this is going to be 1 minus 1. So in other words, it's going to be equals to 1 minus 1, and this can be 1 plus 1 at the bottom, and this is going to be equal to 0. So we have that. So that is equal to 0. The next one. So now the next derivative is going to be, make some more room here. So f prime of x, this is going to equal to, from our derivatives table here. So this derivative of hyperbolic tan is equal to hyperbolic secant squared. So then this is going to equal 2 hyperbolic secant squared of x, like that. And here I'm just going to just remove that bracket, just write it as is. So this is going to be like that, x, just make it a bit easier to see, it's a bit less messy. So now the next one's going to be the derivative f of 0. This is going to be equal to, well, this is going to be 1 over, because remember this is just, scroll up. Yeah, so secant just 1 over cosh. Yeah, so we have that. So that's going to be just similar to our basic trig ones. It's going to be squared like that. And I'm just going to put this, I'm going to put a 0 here. I'm going to put this in bracket squared. So we're going to square that 0. And then this one at the bottom is going to equal 2. And well, we know cosh, that's going to be just e to the 0 plus e to the negative 0. So it's going to be equals 2. And then the top's going to be, I'll just leave it like that. I'm just going to put it like this. And I'm going to write this as e to the 0 plus e to the negative 0 divided by 2, all squared. So then this is going to be 1 plus 1 is 2. Those cancel, so this is going to equals 2. We'll just put it down, 1 plus 1 over 2 squared. So this is going to be 2 over 2. Yeah, 2 over 2 is 1, and it's going to be 1 over 1 squared, and that equals just to 1. Alright, so we have the first two terms for the Maclaurin series. Let's just keep going, and let's take 2 more derivatives. So the next one's going to be, and now we get f double prime of x is equal to, and then using the power rule, the 2 goes down, and then we have secant h like that, and we subtract the power, and then we take the derivative of the inside chain rule, and then this is going to be, derivative is going to be negative secant, negative secant h x, of x times by tan h. This is going to be squared, put a negative, and then tan is going to be put an x, tan h, like that, of x. And now when you plug these inside, so f double prime of 0, this equals to, well, plug in 0, we're going to have negative 2 times by, this one's 1, because we already have that's 1, secant h, it's going to be 1 squared, then the tan h is going to be 0, it's going to be times by 0, so the whole thing becomes 0. So 0 wins. Alright, so we have that. Now the next one's going to be just a bit more, just a bit more tedious. Okay, so now the third derivative is going to equal 2. Now we're going to use product rule and chain rule and some identities just to simplify it as my calculus book did. So we're going to have this, we're going to take the derivative of this one. So let's put this here. It's going to be negative 2, actually negative 4. So we're going to take the derivative of this. This 4 goes down. I mean this 2 goes down. It's going to be 2 times 2 is 4. And then we'll have a secant h. And then derivative of secant h, we'll just put this tan there. Then using chain rule, try to do this all in my head. Now we take the derivative still of this one. And that's going to be negative secant h times tan h. So we put a squared here and a squared here. And now the next one's going to be, now we use product rules to take the derivative of this one. So this is going to be negative 2 secant h squared of x. And we just put that down. And then we take the derivative of tan. Yeah, now derivative of tan h is just going to be, well, we know that already. That is just, so that is just secant h squared. So that's going to be, so instead of the 2, it becomes a 4. Like that. And now my calculus book simplifies it further, but we could just start here. So when you put in the 0 in here, the third derivative is 0. This is going to equal 2. We plug in 0, this is going to vanish. So we'll have 0 minus this 1. Yeah, minus 2 there. Goes negative 2. Like that. Yeah, so we could just end it off like that, but just because the solutions manual simplified this further, or let's write simplified further. I'll just put a side note, because it's not necessary. Simplified further, simplified further by just some more algebra and some use the identity. So what we could do is, all right here, just fix up this writing over there. So now what we could do is take out this, this negative 2. But also before we get that, we forgot one thing here. When we did the chain rule right here, this becomes, so the 2 goes down, 2 times 2 is 4. But then this secant secant h x, the derivative is negative secant hx times tan hx. So there's a plus there. Yeah, so we have that. So now the next step we're going to do is I'm going to take out the like terms, which is this 2 secant squared of x. So we're just going to put equals 2, like that. This is going to equal to 2 secant h squared, and then this is going to be 2 tan h squared of x, and then minus, minus the this one here is going to be 2, and that 2 is gone, so now we're just going to have minus secant h of x, like that, and then just use the identity over here. This is equal to 1 minus hyperbolic tan of squared, so tan h squared. So this equals 2. So then this goes to 2 hyperbolic secant squared 2 tan hx minus, and then this is going to be a minus 1. So it's going to be minus 1. Let's put it like this. Put a bracket minus. This is going to be tan hx, and this is this identity. In brackets. That is just this one over there, and then this becomes. So what this becomes is we'll have a minus 1 there, then this becomes negative, this becomes positive. So then we're going to add up 2 tan h squared, then plus a tan h squared. So we're going to get this equals to 2 secant h all squared times it by 3 tan h x squared minus tan h x and tan h squared x minus 1, like that. And so you could plug in either or. And also you could plug in f triple prime of 0. This equals to, you can just plug that in, it's going to be 2 times 1 times 0 minus 1 equals to negative 2. So again, just because my calculus book had it written like this, but you can just do this one, it's much easier like that. And this form will come in handy too, as I'll go over the alternating series. So anyways, let's go further. Alright, so now, thus from the derivatives, the first term in the Maclaurin series of tan h of x is x, and I'll get to that in a bit. So if the water is shallow, we could use the following approximation. So let's just go, first of all, thus, we have hyperbolic tan h of x is equal to, or actually it's approximately equal to, because we're using an approximation, and using Taylor approximation, this is going to be equal to f of 0. So the first, the 0th derivative is just f of 0. And then plus, just remember that Taylor's expansion is going to be f prime of 0 divided by 1 factorial times x, times x to the 1, plus the next one is going to be f double prime of 0 divided by 2 factorial x squared. I'm just going to make some more room here and write it across here. The next one's going to be f triple prime at 0. It's going to be x 3. The next one's going to be plus dot dot dot. Divide this by 3 factorial. So that's what we have. And we know our values. So f of 0 is 0. Then f prime of 0 is 1. And then f double prime is 0. So yes, we go 0, 1, 0, negative 2. So it's going to equal to, so this is this part's going to equal to 0 plus, the next one's going to be 1, so it's just going to be x, so that's the first term is just x, like that. Next one's going to be plus, and then, the next one's going to be 0 as well. The next one's going to be minus 2. Minus 2 over 3 factorial, and this is going to be x cubed, like that, plus dot dot dot. So now this part's going to equal to, just remove the 0, so x minus 2 over 3 factorial, x cubed, and then it's going to go plus. In fact, it's going to go plus minus, as I'll show in a bit. So it's going to be alternating like that. So now when we plug in our values for x, or in our case it's going to be tan h, and remember ours is going to be 2 pi d over L. So remember the formula. Just scroll all the way up. So we're approximating tan h, and remember tan h is just this 2 pi d over L. So we're going to approximate that. So tan h, and then we're just going to write 2 pi d over L. This is equal to, and let's put this in, 2 pi d over L minus, and now we're going to have a 2 over 3 factorial, just leave it like that, 2 pi d over L cubed now. Next one will be plus minus dot dot dot. And now this, if it's shallow, so if this is small, and yeah, I just want to make a correction there. Yeah, so it does look like the question is stating if it's shallow as in the wavelength is much bigger than this d there. Yeah, so as you can see, that's why even in alternating series part C, it's much greater, L is much greater than d, so 10 times d. So yeah, so if we have that case where this is shallow, so this would be 2 pi d over L cubed, or cubed plus, wherever you get further and further. This goes to small. This becomes very, very small when d is small. When d is less than, much less than the L, like that. I.e. shallow. So it's a shallow pool. I.e. or just put a bracket. Actually, what should I put? Yeah. I.e. shallow. Yeah, so that's what we have is, now we just take our approximation. So now approximation, if we just, all we consider is just this one. So this is all we consider. So, because we're going to assume the other ones are small. So thus, we're going to have tan h of 2 pi d over L is approximately equal to, and then this is going to be, and also this is approximation. Because we haven't seen the error of it yet, even though it goes to infinity. All right, let's go further. This is going to be, just 2 pi d over L. And then we can plug this into our formula, and so our v squared formula number, this one is equal to, let's just scroll up, it's equal to GL, where was it, GL over 2 pi times tan h, and then this is 2 pi d over L. So yeah, the key is GL over 2 pi. So it's going to equal to GL, yeah, so GL over 2 pi times it by, or this is going to be, I'll just put the actually full thing first. So, GL over 2 pi times hyperbolic tan h of 2 pi d over L. And now what we're going to have is, well, this whole thing, so the whole idea of approximation is to get rid of the complex functions like tan, hyperbolic tan h, etc., and just replace it with just, well, this one, just a simple constant. Alright, like 2 pi d over L. So throw that in there. So now this becomes this whole thing. Alright, so then what we get is this is approximately equal to GL over 2 pi times by 2 pi d over L. And what happens is this cancels, this cancels, this cancels, this cancels, this cancels. This whole thing cancels. This is a better, just cancel this, leave the d, cancel these, cancel this. So this is going to equal to GD. So that's what we have. So it equals to GD. So when we take the square root, so thus we'll have thus, and just put an arrow, or actually just leave it. Yeah, just leave it like that. So thus put an arrow. Square root, yeah, so v squared is approximately equal to, and I mean the square part. So the square, so we're going to square both sides. So v is approximately equal to, when you square both sides, it's going to be, well, again, for completeness, it's going to equal to the square root GD plus or minus. We just take the plus. This number you could minus, yeah, minus square root GD times minus square root GD. It's going to cancel the plus. It's just going to be GD. So we'll take a plus for this practical example. So it's going to be GD, just because negative velocity is for a different scenario. So this is what we have over there. And this is, yeah, square root GD. This is exactly what we have. So just check mark. And you can double check that here. Let's scroll up. And yeah, so make sure, yeah, so basically use the Maclaurin series to show that V is approximately equal to the square root of GD. And again, thus in shallow water. And yeah, so they do mean that it's much less than L. The velocity of a wave tends to be independent of the length of the wave. Alright, so now let's take a look at part C, and this one asks, use the alternating series estimation theorem to show that if L is greater than 10 times D, then the estimate V squared is approximately equal to G. D is accurate to within 0.014 GL. Alright, so now we can continue further, and basically part C is looking at the error associated with this approximation with it, which is, you could also write it as v squared as approximately GD. Anyways, let's just keep going further. Now, I just want to make a note here. So, part C, so MES note, although the exercise implies that the Maclaurin series for tan h of x is alternating, I couldn't obtain a formal proof, and I am not sure what my calculus solutions in my calculus book, solutions manual means by their sentence. This is in the solutions manual I somehow have. Since tan h of x is an odd function, its Maclaurin series is alternating. So that is the statement for it, and I will look into this in the future. So stay tuned for that because I'm not sure what this means. I'm trying to decipher it, and I'm not sure how they just jumped from odd function to Maclaurin series alternate. Anyways, continuing further. So recall the alternating series estimation theorem from earlier. Here's a link to it again. And I'm just gonna review this again. So alternating estimation theorem. So if S is the sum of an alternating series that satisfies, where the alternating signs are included separately here, so that you have their Bn is always positive. So satisfies these two conditions: I, which is Bn plus 1, is greater than or equal to 0, and less than or equal to Bn. That is the next term. Each successive term is less than the previous. So Bn plus 1 is always less than Bn. And also the limit as n approaches infinity of Bn is approaching 0. Then the remainder r sub n, absolute value, is going to be which equals to the difference between the exact sum and the difference between the exact sum and the partial sum, the Sn. The absolute value of it, S minus Sn, is less than or equal to the next term, so Bn plus 1. Yeah, so thus in our case, our estimation for tan h of x has a remainder less than the first neglected term of the series. So if we just recall, this is write down our tan h approximation. So tan h 2 pi d, right without that because we've been doing that so far, 2 pi d over L. So if we scroll up to our estimation, so this was in part B right here, where we looked at the first term here, and then it's going to be alternating, and so then we have so this is small, 2 pi d over L, because we have d is much less than L, and then the successive terms are getting smaller and smaller, and obviously it's going to be going towards 0 as this goes to infinity as each term. So this is our approximation, and our first neglected term is this one here. So that could be we're going to use this for our estimation, alternating series estimation theorem, and this is the first term there. So let's just write down what we have. Yeah, so back here, so tan h 2 pi d is approximately equal to 2 pi d over L, and then minus 2 over 3 factorial, and then we have the 2 pi d over L, this is cubed, plus minus dot dot dot. So it's alternating, and these terms are each successive term. This is our Bn, so this would be our Bn B1, and then this whole thing would be our B2, like this, and then so we account for the negative signs there. So these are all positive there. All these values are positive, so this is our B2, and this is all approaching 0. Yeah, this is approaching 0 as each successive term. So limit as n approaches infinity of b sub n goes to it's approaching 0, and this is each term is getting smaller and smaller because d is less than L, and you have this fraction, this power here. So this is a fraction, where d over L is going to be less than 1, and you keep taking the power, it's going to be multiplying by less than 1, multiplied by less than 1, it's going to get smaller and smaller. So thus we have, in our case, r sub 1, so the remainder associated with using this right here, using the first term approximation, is going to be less than or equal to, well, B2. Less than or equal to the absolute value of this one there, which is just B2. Like that, because it's positive. And then this equals to 2 over 3 pi, like that. And then 2 pi d over L cubed. Alright, so now that we have this, the next step is, well, we know in the part C it says use basically to show that if L is greater than 10 times D, then this estimate is accurate within 0.14 GL. So we're going to put this term in there. So let's see what we get now. So we're going to write if L is greater than 10 times D, then what we end up having is then the remainder of using the first term R1 is going to be less than or equal to, well, it's going to be less than now because, so if L is greater than 10 over D, then this number here is going to be, it's going to be larger than this value. And the larger the value, because you're dividing by it, it's going to get, this overall all one's going to be smaller. So in other words, this is going to be less than. So the remainder is going to be less than when you have 2 over, I'll just factorial this out, 3 times 2 times 1, and then you'll have, so we can cancel out the 2. So move this like this. So we cancel this and this, and it's going to be 2 pi d over 10 times d. So yes, this is going to be less than this one because when this is a very, very large number, this gets smaller. Well, so then L is greater than that, so then this is going to be, so the remainder is going to be less than this thing because it's going to get, this whole thing's going to get smaller and smaller. So again, the maximum value of this right side is for when this part right here is at a minimum, which is this 10D because L is always greater than it. So then now we could just cancel this and this. This will cancel, this is going to cancel, we're going to get a 5. So this equals 2 pi. I'll just put just put it like this: 1 over 3 times it by pi over 5. Actually, we forgot to cube this whole thing. So cube it. So we're gonna get pi cubed over 5 cubed, which is 125. This is just 5 cubed. And also we know 5 times 3 is gonna be times 2 is gonna be 250. And then add another one is going to be 375. So this is going to equal to, let's put this, let's put it like this. Let's just put it here. So this is going to be less than 1 over 3, and then pi 3, let's remove this 1 over 3, it's going to be 1 over 375. Times it by pi 3. Times it by pi 3. So 3 times 125, 250, then 375. Like that. So this is our remainder for that approximation of tan h 2 pi d over L. Alright, so now that we have this, I just moved it over there to make some room. We can now estimate the accuracy of our approximation. V squared is approximately equal to GD, and let's just write this all out in a summary fashion. So if we have our exact value, just our equation V squared is equal to GL over 2 pi tan h 2 pi d over L. Then our approximation that we used the first term of the Maclaurin series for tan h, like that. So then our approximation was V squared is equal to GL over 2 pi, and then we just used the first term, which was again 2 pi d over L. So then this would go down over here, 2 pi d over L, and we replace the tan h. So then as per usual, this all cancels, we get equals to GD. So then now this error in this approximation is, this approximation right here, this 2 pi d over L, this is accurate within, so within or less than pi cubed over 375. So if this part's accurate within pi cubed over 375, then the error, so then our net error is going to be using this approximation. This approximation is going to be less than, less than, then just multiply by this this full thing. So you're going to multiply this by this error of this one to get the full v squared error. So this is going to be, error is going to be less than GL over 2 pi times it by pi cubed over 375, and this is going to be, this will cancel, this will cancel. That doesn't really make anything that much simpler, so we'll just keep it in there, and then we're just going to calculate this out. So if you calculate this out with the calculator, this would equal to less than point, or just approximately. I'll just put an approximate because it's less than it. Yeah, this is approximately equal to, and you plug into the calculator 0.00, or just one of the zeros, 0.0013, and then it goes to 2 times by G times by L. And this one here, if you plug this into the, well, this one is less than our 0.14, as I'll scroll up here to what we were asked. We were asked to show 0.014 GL. So 0.0132 is less than it, and I'll show you the calculation check in a bit. So yeah, this is going to be our less than 0.014 GL. Yeah, here I just move that over. I'm just going to box this out, this whole thing out like that. Alright, and here is a quick calculation check for this, and so calculation check pi cubed divided by 2 times pi, times 375. So you have the pi cube on top, and the bottom is 2 pi, and then 375, and then put this in a one-note calculator, like this, space, equals, space, and it gives you this giant, giant number, and you got the first three there. So 0.013, and then this rounds up. This 15 goes to 2, and and then you have the GL there. Just include the GL.